Lecture on module 4, diversity. In module 4 we will be looking into, or we will be studying, what is diversity, what is equalization and multiple access. First let me explain to you the concept of diversity. Diversity means that you are sending multiple copies of, so let us consider a transmitter here. It is transmitting a signal and received here at the receiver. Okay. Let us consider a case where the information or the signal that is passing from transmitter to receiver through a wireless channel gets broken, and you have a path, it is broken and you don't have the signal that is being transmitted reach the receiver. In diversity, what we are doing is that, in the concept of diversity, what we are doing is that we are sending multiple copies of the information from one point to the other. From the transmitter to receiver, you are sending multiple copies, so that in case you miss out a single path, if this path is broken, still the communication system is not getting affected, so that we have multiple paths. This data is being transmitted from here to here through other different paths. So in diversity, by diversity what we mean is that we have multiple copies of the transmitter information that is being transmitted to the receiver through different means. We have different types of diversity. We will be going through all the different types one by one. So this is called as diversity. Why diversity is important? Because we, in our 4th generation and 5G, we have a very innovative new concept called as multiple input, multiple output, MIMO. I'll give you an introduction to MIMO, what is MIMO and its details, but we will not be studying in depth because we do not have it in our syllabus completely. Okay. So let us consider a transmitter called as TX. This is called as input, I. This is a receiver, and when a signal is transmitted from transmitter to receiver, and if there is only a single path, it is called as SISO, single input, single output. If you have multiple receivers and the transmission is happening in this fashion, you call it as single input, multiple output, SIMO. If you have multiple transmitters but a single receiver, you call it as MISO, M-I-S-O. When you have multiple inputs and multiple outputs, when you have an array of antennas transmitting and an array of antennas receiving, we call it as multiple input, multiple output system. I hope all of you are very clear with what is single input, single output, multiple input, multiple output, and all the different types of diversities. Okay. Now my question is that why do we want to have multiple inputs? Why this diversity is being, or why the concept of diversity is being developed? The basic necessity for diversity is to counter fading effects. Fading reduces the power of the transmitted signal. So in order to compensate for fading, we are using different diversity techniques. So according to our syllabus, we will see what are the things that we need to study. Let us have a briefing about the syllabus. Receiver diversity, selection combining, maximum ratio combining, transmitter diversity, Alamouti scheme for 2x2 MIMO. This is the first part, 4.1 of your syllabus. You are going to study what is the basic why we need to have receiver diversity, or what is meant by receiver diversity, selection combining, maximal ratio combining, transmitter diversity, Alamouti scheme for 2x2 MIMO. In this particular lecture, we will be seeing only introduction to receiver diversity. The next class we will be studying what is selection combining, maximal ratio combining, and so on. So what are the different types of diversities? There are very common methods. Actually, diversity we are classifying into 5 different types of diversity. One, we call it as spatial diversity. Spatial diversity, very simple. You keep different antennas at a different space. You give some space for different antennas. Temporal diversity, I can draw an example here. Let us consider only the receiving antenna. Let this be one, let this be another one. You have a space here. You call it as spatial diversity. The second case, temporal diversity. In temporal diversity, let us assume that this is the receiver. A signal is transmitted at say 0 seconds, then another one 0 plus at one tau, which is a small time gap. So at different time intervals we are transmitting signals. We call it as temporal diversity. Similarly, when we change the carrier frequency, you have a signal here with one set of carrier frequencies, another with another band of frequencies. You have frequency diversity here. So these are syllabus. The next fourth type of diversity, angular diversity, very easy. Different antennas at different angles. You keep different antennas at different angles, you receive multiple copies of the same information. See, you should keep in mind that whatever is the information, signal SI of t that you are transmitting is same. You are not transmitting different information or different sets of values. All message bits that you are transmitting would be same. Polarization diversity, we will have vertical and horizontal polarizations to be used for diversity techniques. So these are the 5 common principles with which we work on we have 5 different types of diversities. First one is called as the spatial diversity, temporal diversity, frequency diversity, angular diversity, and polarization diversity. Diversity means multiple antennas. Okay. Now, you know what is, have you heard of what is NR? NR is a new concept. What is that? Have you heard of it? 5G, very good. 5G, new radio. NR stands for new radio. Advanced techniques where we have radio access networks. Okay. So, multiple antenna systems are extremely important in 5G wireless communication systems. So, we are using multi-antenna systems, the concept of diversity in different advanced technologies. So, it is extremely important for you to understand what is meant by diversity and what are the different methods with which we are going to implement diversity techniques. So, why do we need to have, or why do we need to think of diversity techniques? This is for your exams, maybe you may get questions based on this. So, for the answer you can write that fading reduces. So, what is the need for diversity techniques? First point is that fading reduces the power performance of wireless channel to a great extent. That means that fading reduces the signal to noise ratio of the receiver at the received end. In diversity, what happens is that we send the same signal through multiple paths, and these independent paths are combined in such a way that fading of the resultant signal is reduced. Once the diversity branches are generated, then what happens is that it must be combined together, right? That is called as diversity combining. So, the need for diversity is that the fading will cause loss of power. The signal to noise ratio will be considerably or drastically reduced when we have a signal that is being transmitted from one point to the other. Diversity combining is done to mitigate the effects of fading in wireless channels. Okay. Now, diversity exploits the random nature of radio propagation by finding independent signal paths for communication. So, it means that, see, when you transmit a signal from one point to the other, it is being received at one. If all the signals travel in the same fashion, diversity will not work out. Am I right? Yes or no? Since we have multiple paths, we have different antennas, we have different locations, changes in the signal, we have diversity. That's why we have one signal having higher power. A signal is transmitted from one point to the other, it travels through different paths. That is called as multipath propagation. Each path will have a different signal to noise ratio at the receiver's end. That is why we have diversity coming into the picture at all. Okay, if all the signals are traveling in the same fashion, all the received signals will have same signal to noise ratio, and we don't have anything to do with diversity. Am I right? We have different parts with different signal to noise ratio, and we have this property of random nature of this radio propagation, so that we'll have different independent signal paths with different values. So we'll have a small understanding about a review about what we have already studied. What is small scale fading? Because we'll be doing most of these mitigation techniques for small scale fading. So small scale fading refers to the rapid changes of amplitude and phase of a radio signal over a short period of time, on the order of a very small time, that is a very few seconds or a very short distance. We have already studied what is small scale fading. We just want to understand what is small scale fading because we are going to do different mechanisms to mitigate small scale fading. So here you can see that whenever we have an increase, see, same signal can be, this is a graphical representation of small scale fading for different pulse and amplitude for a same signal with different paths. You have a signal where you can imagine this to be a line of sight communication where you have the highest amplitude and a different phase. As the signal propagates through different multiple paths, you have that signal fading, and the fading extends from very small to very high level. Okay. So let us assume this particular slide is for you to understand how far a small scale fading can affect the entire communication. If one radio path undergoes a deep fade, another independent path may have a stronger signal. By having more than one path to select from, both the instantaneous and average signal to noise ratios at the receiver may be improved up to 30 dB, as high as from 20 to 30 dB. So minimum there is an improvement of 20 dB in the power and can go up to 30 dB because it mitigates the effects of small scale fading to a great extent. The same the next point in our syllabus we will be studying what is receiver diversity. The name says that if you are employing diversity techniques to the receiver, we call it as receiver diversity. So we'll study some, or we'll give some definitions for what we are going to do in future. Okay. The next thing what we are going to study is selection combining and maximal ratio combining. These are two different techniques of combining these diverse signals from different points. Before that, we'll have a small introduction to what is receiver diversity, how receiver diversity is going to improve. So this is an introduction to the next two lectures, or next two topics basically, which is called as selection combining and maximal ratio combining. So let us consider a system where a received signal, we have a set of received signals from 1 to m. Okay, let this be the receiver 1, receiver 2, and so receiver 3, and so on up to receiver m. So this is called as an m branch receiver diversity. You have a multiplier, a component to find out the weighted sums. We call it as alpha 1, alpha 2, alpha 3, like that up to alpha m. All these signals are received at a receiver combined, and the combined output signal to noise ratio is given or denoted as gamma sigma. Gamma sigma means the sum or the received signal in general, in total, okay, with the respective weighted averages, weighted sum of different fading paths. So let the signal received at this antenna, let us call it as R1, be equal to R1 e raised to j theta 1 Si or S1 of t. S1 of t means the signal that is being transmitted through the first path. S of t is common throughout. Okay, we are transmitting the same signal, but we are receiving different signals at the receiver's end. We have values from R1 to Rm. The output of the combiner is the weighted sum of different fading paths or branches. When all complex values of alpha I except 1 is 0, then the combiner output will be that of alpha I. So let us imagine that we have here this one be alpha 1, alpha 2, alpha 3 and so on, and except for 1, let us consider this to be alpha I. Except for alpha I, if all these multipliers are 0, the only output that we receive will be that of alpha I. If more than one of alpha I is 0, then the combiner adds together multiple paths. Through each path may be weighted by different values. Okay, if there are multiple paths, we will be taking the sum of all these paths with a weighted value. So the main purpose of diversity is to coherently combine the independent fading path that affects the fading are mitigated. So here what we are going to do is that we are going to combine more than one branch signal, and this requires a process called as co-phasing. What is co-phasing? We'll be seeing as we go on, where the phase phi1 of the ith branch is removed through multiplication by a factor called as alpha I, which is equal to ai e raised to minus j theta I for some real valued ai. The phase removal requires coherent detection of each branch to determine its phase phi1 or phi I. Without cophasing, the branch signals would not add up coherently in the combiner, so that the resulting output could still exhibit significant fading due to constructive and destructive addition of signals in all branches. So here what we are going to do is that first we have diversity, the signal, the same signal being received by different antennas or different receivers. Okay, the next stage after this same signal being received is that you will be analyzing the combined output and finding out which is the most suited output that can be used by the receiver to determine the originally transmitted signal. Okay, this process requires what is called as co-phasing. As it is generally understood, so this is called as co-phasing. What is co-phasing? A branch, that is a phase phi of the ith branch, is removed through multiplication by a multiplicative factor. We call that factor to be alpha I. In that case, the combined output at the combiner is given by S of t into gamma sigma, where S of t into alpha sigma, where we are adding up all the weighted sums. The alpha is nothing but ai into e raised to j 2 pi phi 1 into st, right? So we have the signals that is being added up. So we have this alpha sigma is equal to sigma I AI Ri. Then in that case the signal to noise ratio gamma sigma is a function of the number of diversity paths, the fading distribution on each path, and the combining techniques. We have we have 4 common types of combining techniques, out of which we are going to study only 2 combining techniques. Let us assume that there is no fading. In that case, the received signal, the Ri, will be equal to root of Es, the energy per symbol of the transmitted signal. We are assuming a condition where there is no fading or there is no loss of power. In that case, we are assuming that the received signal Ri will be equal to the root of Es, the energy per symbol. And in case, as usual, for all the previous derivations we have done, the power spectral density is denoted by N0 by 2. In that case, the received signal to noise ratio gamma sigma will be given by gamma sigma is equal to sigma I is equal to 1 to m AI Ri whole square by n naught into sigma I is equal to 1 to m AI square. Substituting the value for AI Ri is root Es, AI is 1 by n naught, sorry 1 by root n naught. On substituting that, we will get the signal to noise ratio, the combined output at the combiner output, that is gamma sigma is equal to m times the Es by n naught. That means that while using diversity techniques, the number of diversity techniques, here we are using an m branch diversity, right? The SNR is multiplied that much number of times when compared to a single receiving system. So the significance of receiver diversity, maybe you may get a short question or something relative, how significant is receiver diversity or what happens to the signal to noise ratio while using an M branch or N branch or whatever it is diversity. That means the sum of the signal to noise ratio increases that much number of times. So here we have come to know that gamma sigma is equal to m times Es by n naught and increases m times in the absence of fading due to coherent combining of m signals received from different antennas. This signal to noise ratio increase in the absence of fading is referred to as antenna gain and is defined as, see, antenna gain or power gain. Array gain or power gain. Array gain or power gain. Array gain means what we are gaining through diversity. The number of things. So, array gain is a very important definition. You may be asked a question about defining, how to define array gain or what is array gain. In other words, array gain is also called as power gain. So in case you get a question in your exam asking them about what is power gain, Don't get confused. Array gain, other name is power gain. So mathematically array gain is defined as AG is equal to gamma sigma by gamma average. This SNR increase in the absence of fading is referred to as the array gain and is defined as the increase in the average combined signal to noise ratio gamma sigma over the average branch signal to noise ratio. So average SNR. I think you remember that the bar denotes the average value, right? The average value of SNR to the average branch SNR. Now the next two things is about how shall we measure the performance of diversity. So I told you that diversity techniques are used so that if there is any breakage of the signal or in the way if the signal is lost or missing or something happens to the signal, how it is being received in the receiver's end. This is the problem, right? So one thing what we have studied in the third module is about outage probability. The probability that a signal that is being transmitted from one point to the other is not at all received in the other end because the signal to noise ratio is below the threshold value. The threshold value is denoted by gamma naught. Am I right? I hope you remember that. I hope you remember that we need a minimum threshold valence. So now let us use these two terms. One is called as PS and the other one is P out to measure the performance of the diversity system. PS is equal to integral 0 to infinity PS gamma P gamma sigma gamma D gamma, where PS gamma is a probability of symbol error for demodulation of the signal S of t in an additive white Gaussian noise with SNR gamma. Outage probability, second definition. We have seen two factors, right? One is called as PS, the other one is outage probability. Outage probability is defined as very simple. P out, the sum of the combiner output is less than the threshold value, right? Gamma naught. Less than or equal to gamma naught. That is equal to 0 to infinity P gamma sigma of gamma D gamma. So we have defined what is outage probability. How do you analyze the performance of a diversity system? Another important definition called as the average probability of error for diversity systems. We define PS as C, the average SNR raised to minus M, where the M is the order of the diversity. We have M branches, right? C is a constant that depends upon the specific modulation and coding, the average received SNR per branch, and M is the diversity order of the system. The average probability of error can be a question. So we shall wind up this particular lecture with this. Thank you all for patiently cooperating, and now the next class we will be seeing selection combining. How we are going to combine the different branches of the received signal through diversity. Is there any questions for you to ask? Any doubts? Any queries?